Hello everyone. So today we are going to discuss about how MIMO NOMA can be used in VLC. In the earlier classes we have discussed about NOMA and how NOMA can be used in visible light communication systems. So today we will discuss VLC in using MIMO and NOMA. So as you see in this slide, this is a 5G network architecture. So currently 4G technology is fairly stable. Different countries are migrating to 5G network, and 5G gives you high data rate as compared to 4G. For example, there will be 1,000 times more capacity, system capacity, 10 times higher throughput, and they are 10 times energy efficient as compared to 4G systems. So these are the goals of 5G network: energy efficient. And this is required because the newer applications are all bandwidth thirsty. For example, virtual reality, safety applications, healthcare, IoT. So these are the applications, and these high or these features like 1,000 times more capacity, 10 times higher throughput, 10 times energy efficient is basically will use software defined networking, will use massive MIMO devices, device to device communication, very small cells, and machine to machine kind of applications, vehicular to vehicular applications, and also cloud RAN. So these are the technologies which are being used in 5G. Now in RF, there are a lot of papers which are MIMO NOMA based, and the challenge is how to assign power allocation, efficient power allocation with low complexity in RF is a challenge. So we will see the applications of MIMO NOMA in VLC, and we will see that the power algorithm which are used are fairly simple, or they're simpler as compared to RF power allocation algorithms. So just to revisit uplink and downlink NOMA. So this is a case of downlink NOMA transmission. So in this case, there are two users, for example, user N and user M, and they have different power levels. User 1 has this much power level, user M has higher power level. So you do the SIC, that is SIC operation, successive interference cancellation at user N. So first you detect the user M, which is high power, and then subtract this user from rest of the signal. You will get the signal of user N. So this is how user N is detected, and this is user M. So the SIC operation, successive interference cancellation, is performed at the user level. So this is a downlink transmission, and in the uplink transmission, you have two users, user N and user M, and the SIC operation happens at the base station. And so at the base station, first you detect the user N because the signal is coming at a higher power level. So user N detection is done, and then this is subtracted from the signal, and you are able to detect the user M. So this is example of uplink. So in downlink, the SIC takes place at the user end, whereas in the uplink, the SIC takes place at the base station. And the performance gain for uplink and downlink, they're different. So this we have already studied when we were discussing about the NOMA. So you can have not only MIMO, but you can have different versions of MIMO. So one of them is single input, multiple output. So in this, what happens, suppose this is the base station and these are the users U1, UL, U capital L, they are connected to these base station. So this information is superimposed here, and then at the receiver end you have U1. So there can be multiple antennas at the receiver. So this is a case of a single input and multiple output, and this say has H1 as the channel coefficient. Similarly, say for UL, channel coefficient is HL, and then you have capital L, so this is H capital L. So in this case, you get three inputs. There are NR receivers and one transmitter. So in this diagram, there are three receivers. So one can use MRC, maximal ratio combining technique, to detect the signal which is coming from here, and then within U1 you can do SIC operation, successive interference cancellation, to recover the signal for U1. Similarly, you can do for UL, and U capital L for different users. So this is a case of single input and multiple output. So this gives you better performance gain. So this I am talking in the context of RF, and this also gives good diversity. So these are the advantages. We will see how some of these things which have been used in RF can be used in VLC. So this is a case of single input, multiple output NOMA. So these are some of the results of NOMA, single input, multiple output NOMA. So if you see, this is user 1, this is the rate for user 1, and this is user 2. This is rate of the user 2. And the sum rate is given by this curve. This is the sum rate. And if you see the conventional orthogonal multiple access, that is OMA, which is given by this. This is, I would say, OMA. So this is sum rate. Basically, it is NOMA. So you see there is a clear advantage in NOMA as compared to OMA. And the other lines, which are the dashed lines, this one and this one, these are the lower bound sum rate and upper bound sum rate. So using MIMO NOMA. So this is the performance gain you get as compared to conventional orthogonal multiple access schemes. There is another possibility of using NOMA in a MIMO context, which is called as cooperative NOMA. In this, we use a relay, and the relay basically will give you increased coverage area. Increased coverage area, and also it will give you high increased system capacity. Increase system capacity. We will just see how this is possible. So increased coverage area, basically if your users are far away from the base station, one can put a relay in between. The relay could be of amplify and forward type, or it can be decode and forward type, and also it can be half duplex or full duplex. So by putting a relay, you basically can increase the coverage area. And also because you are directly interacting, or the base station is directly linked to the relay, so multipath fading is also avoided. So let us understand through a diagram how this NOMA using relay can give you advantage in terms of increased area, increase of and also increase of system capacity. So first I am discussing a coordinated direct and relay transmission direct link. So suppose this is your base station. This is the antenna, and relay is somewhere here. This is relay R, and suppose your one user is here. This is a user 1, and this is a user 2, and they have their antennas here. So there can be a direct transmission to user 1. There can be a direct transmission to user 1, or there can be a transmission first from base station to relay, and from relay to user 1, and from this relay there is a transmission to user 2. So this dashed line, actually I'll just explain this. So this is the antenna for user 1, and also so let me put the arrow also. This is the direct transmission to relay. This is direct transmission to user 1, and you can have transmission from relay to user 1. And this is the direct transmission to user 2. So by putting this relay, you are able to increase the coverage area, and also the performance can be increased because U1 is getting signals directly from the BS, and also directly from the also getting signal from the relay. So this might result in increase of system performance or system capacity. So this is an example of a coordinated direct and relay transmission direct link. The other could be a cooperative scheme without direct transmission, without direct link. So this example could be, for example, this is your base station, this is the antenna, and then you have the relay here, and this channel coefficient is, so this is a S, so this will be HSR, and there are many users connected here or here. So this will be HRU1, HRU2. This is channel coefficient. This is user 1, user 2, user 3. This is HRU3. So this is a cooperative scheme without direct link. So there is no direct link to the user, but it is through a relay. So this is another form of cooperative NOMA. So the signal, the NOMA, actually the NOMA is performed at the user. So the SIC operation, SIC is performed at the user level. And I'm assuming the signal, which is actually power domain NOMA, is getting transmitted from the base station, and the SIC operation is being done at the user to extract the data for that particular user. Similarly here, the SIC operation is happening here, and here you get superimposed signal, that is, power domain NOMA. And by doing the SIC operation at the user, you are able to get the data of respective users. So this is an example of cooperative NOMA. Now there is also a possibility of cluster-based MIMO NOMA. So in this case, what happens? Suppose the users are spread over in this area, and this is, for example, the base station here. This is the antenna. So these users which are in this area, they are actually grouped. So for example, this could be from UN to UL1. So this is cluster 1. This is cluster 1. And similarly, there can be another cluster. This will be, say, U2 to UL users in the cluster 2. This is cluster 2. This is cluster 1. And similarly, you can have cluster M or different clusters. So the beam formation is done in such a way by using transmit precoding and detection, so that the users from cluster 1 and other clusters, there is no interference from other clusters. That is, intercluster interference is avoided. And within the cluster, one uses NOMA technique to handle the interference which is caused by the other users. So NOMA technique is used to cancel the interference which is caused by the users of that cluster. So intercluster is by beam forming using some sort of transmit precoding, and then this way you can avoid an intercluster, but within the cluster or intra-cluster, one can use NOMA technique to avoid interference from other users. So this is another example of MIMO NOMA, which is cluster based. Now let us shift how these MIMO NOMA can be used in the VLC environment. There is a lot of work which has been done in the RF environment, and how these architectures or the MIMO NOMA can be used in OWC environment or optical wireless communication environment. So for that, let us try to draw a downlink DCO-OFDM based. We have earlier, when we were discussing about OFDM, we had discussed about DCO-OFDM and ACO-OFDM, and here I intend to use DCO-OFDM, and we will use a MIMO and then power domain NOMA, and the channel is going to be a visible light or optical wireless communication system. So let me draw the diagram for this kind of system. So this is DCO-OFDM. So I'm not drawing the internal details of DCO-OFDM that we have done in earlier classes. So this is DCO-OFDM, and this is a user 1 data, which is divided into 2 parts. This is the other part, DCO-OFDM. This is the other part. So user data is divided into 2 parts, and then let me denote this as S11, where this 1 basically tells the user, this is user 1, so user index, and this one tells the first part or first, this is a 1, this is 2, so this indicates this part of the data, the first part of the data. And similarly this, so we can have user k here. Let us draw one. So you can have k number of users. So this is user k data, and similarly it is divided into 2 parts. This is DCO-OFDM. This is DCO-OFDM. And there are in between other users. So we are drawing the first user and the kth user. So there are other users also. So this is S11, and this data goes to a unit which is power domain superposition, and we are also giving DC bias because here I am using DCO-OFDM. So in order to make the system unipolar, we need to give the DC shift, so that the bipolar, which is normal OFDM signal, which is bipolar, first you make it real from complex by invoking Hermitian symmetry, and then you give DC to make it a unipolar. So some DC bias is given to make it unipolar. So this signal will go to this and this block, and then there are from other users, this is from the kth user, and this will be S1, the first part of the signal of the kth user. Similarly, I am drawing here, this is power domain superposition, and DC bias. So this signal will go here, and this will be the second part of the signal. This is S, and coming from the user 1. And similarly, this part of the signal is S, the second part of the signal, and coming from the user K. And there are many points in between. And this combined signal, the power domain superposition with DC bias, let us call that as X1, which goes to the LED. Now you are able to modulate the LED because you have already made the input signal real and unipolar. And similarly, this, let us call this as X2, it goes to a LED. And then you have the channel, this is transmitted through LED, and then you have set of photo detectors. So I am using here 2 LEDs, and then photo detectors are here. So these are the PDs, photo detectors. And this LED output will go to this photo detector, will go to this photo detector, will go to this photo detector, similarly here. And this LED output will also go to these photo detectors. So I am denoting this as from the kth user as from the second LED through a dashed line. And the signal, which output signal of the photo detector will be Y11. So this one actually corresponds to the LED number, LED index. And this Y1 is index of the output. This is output index. So let me write the output index. So, and this will be Y21, this will be Y12, this will be Y22. And then this signal is given to this signal is given, and there are many blocks in between. So this is given to MIMO DMUX. And you do the SIC operation here. Similarly, this is MIMO DMUX and SIC operation. And after doing this demultiplexing of the signal and doing SIC, successive interference cancellation, what we get is DCO-OFDM demod. It's a reverse process. And similarly, for the other streams, DCO-OFDM demod. And similarly, you can do for this user. So this will, there will be one more block here, and then there are many here in between. So this is DCO-OFDM demod, same as earlier, DCO-OFDM demod. And from here, you get the user 1 data. User 1, and then similarly you will get user K data. So you are using multiple LEDs. Because normally in a LED lamp, there are arrays of LED. So it can be used as multiple transmitters, so multiple LED. So this multiple LEDs and you are using multiple detectors. So this will result into enhancement of the spectral efficiency, enhancement of spectral efficiency by using multiple LEDs and multiple photodetectors, spectral efficiency, and you are able to do spatial multiplexing by splitting into two groups, and each group is served by a specific LED. So basically you get multiplexing gain as well as improvement in the spectral efficiency by using MIMO power domain NOMA, and we have used, this is optical wireless channel. So the issue here will be how to do the clustering and user clustering, and how do you allocate the powers. These are some of the challenges with this architecture, allocate power. But this has been simulated, and there are improvement or performance gain which are required for 5G systems. So it basically uses DCO-OFDM, which is a kind of OFDM technique in tuned for VLC, and then uses MIMO. So here you are using two LEDs and two photodetectors. So it's a MIMO system, and it is a power domain, and for extracting the information from the superimposed signal, you are using NOMA technique. So this has advantages in terms of enhancement of spectral efficiency, special demultiplexing, and interference you are able to avoid using NOMA technique. So let us try to do some calculations using a small example where I am using 2x2 MIMO NOMA based VLC system, and there are K users. So system diagram is something like this. This is a LED 1, this is a LED 2, and then you have users here, and each user has say 2 photodiode. So this is a 2x2 MIMO system, and similarly here. So this is a user 1, this is user say small k, and this is user capital K. And let us see the area covered by LED is something like this. And let me define user 1 as the reference. So this is a reference, and the distance between user 1 and user K, the last user, the capital K, is say R, and the total coverage area, the total cover area where LED 2 light is available, that is say capital R. So we will try to normalize, we will see how the signal is received at different locations by using these quantities. So it is a 2x2 NOMA based system, and we are using NOMA technique with K users. So this is a system model. Let us try to analyze this. And signal from LED, this is actually the area. So the signal which is falling onto, for example, user K will be to the other receiver, and similarly from LED 2, which I am denoting by a hard line. So this is the light falling from LED 2 on the 2 detectors, and similarly this is the light falling from LED 1 to the 2 detectors. Now having, so we'll try to analyze performance for this 2x2 MIMO NOMA based VLC system with K users. So the signal XIT, this XIT is input signal to the LED. Input signal to LED 1 or 2, LED I. So this I can be 1 or 2 in our case, is equal to rho IK, and this rho IK is actually the electrical power allocated to the kth user, in the ith LED. So rho IK is electrical power allocated to the kth user in the ith LED, and this is Xi is the input signal to LED I, where I is equal to 1 and 2, and this SI KT is signal intended for the kth user in the ith LED. So as we know, I is equal to 1 and 2, and this K goes from 1 to capital K. So this is the input signal, and this is the DC bias which we have given, because we are using DCO-OFDM. So this is the DC bias. So this is the input to the signal LED I. So if I sum over all the users, because this is electrical power given to kth user from the LED I, if I sum over all the users, I get total P electrical. And I can put this as equal to 1 without loss of any generality, because this is going to be a constant. So I can put this as 1. Now the receipt power Yk by the photodetector is, this is a responsivity. And this is optical power which is falling onto the photodiode, optical power. And this Xi is the modulation index. And this is a channel matrix. In this case, it is going to be a 2x2 matrix, channel matrix. And this is the data, input data. And this is the noise component. So the receipt power is sum of this, which is actually normally you have receipt power is Hx plus N, where N is the noise, H is the channel coefficient, X is the data. But we have also included responsivity, because it is the power is in optical domain. So we have included receipt power, responsivity, and the modulation index. So this becomes Yk is equal to gamma P opt Xi Hk X plus Nk.